So in previous class, actually we talked about the kinetics process is involve the rate of state function evolution, which means the state functions do change with time. So the state function here included the free energy, included the hampers free energy, Gibbs free energy, and all the entropy. And also, if you want to observe the kinetics process, that definitely you need to push the system to deviate from the equilibrium state. Then the process from deviated equilibrium state toward to equilibrium state, this process is what we call the kinetics process. The corresponding path and the path you choose and corresponding rate it happens is what we are interested in the kinetics process. And which parameters is going to affect this kinetics process? That will be the first one. First of all, will be the driving forces applied on the system. And the second one will be the inertia of the system. In material systems, inertia of the system usually will be related to the specific material properties, depending on what kind of flux we're talking about. And in previous slide, actually, we give you 3 examples, including the melting process, creep, and grain growth process. And hope you already can identify what is the driving forces and the inertia of system involved in each of them. So now we are going to move forward. So talking about the driving forces applied on the material systems. So the driving forces were proportional to the degree of deviation from the equilibrium state. What this means, so I'm going to give you an example. If now I have a blue ball, I just put this blue ball on the floor and I'm not going to touch it. So now the blue ball is in the equilibrium state, right? So next I'm going to push this blue ball or move this blue ball to the platform with height h. And now this blue ball gets additional potential energy of mgh, right? So next, I'm going to, so now at this stage or state, I will say, now the blue ball is at deviated state, which is deviated from the equilibrium state because the blue ball is out of equilibrium or deviated from equilibrium state, right? And now it has additional potential energy. Then next, I'm going to do what? I'm going to release this blue ball. So next, this blue ball we're going to falling down or move, or you can say like moving down toward to or back to the flow, right? So during this process is definitely a kinetics process. And what's going to happen during this process will be the energy will be converted from the potential energy to kinetic energy, right? So kinetics process actually is a process which involved from deviated state moving toward to equilibrium state. This is a kinetics process, right? And the driving force is very easy to express. We'll express as the minus gradient of potential energy, right? Okay. So here, so based on this, you can think about that. So the driving force is related to the potential energy in this case, right? So if I move this blue ball toward to higher platform, like this high is higher than this, then the driving force will be larger than this one, right? in this case. So the driving force actually is proportional to the degree of deviation from equilibrium state. So when the platform actually this state with a higher platform one actually has a higher degree of deviation from equilibrium state compared to this one, because it has a higher potential energy compared to this one, right? Okay, so next I'm going to give you the other example, talking about talk more about the energy barrier or system inertia here. So this example would be what? Will be the phase transformation. So now what we have is we have alpha phase, and we're going to transform or react becomes to beta phase. So let's take a look on these figures. Will be the vertical axis will be the free energy part, and the horizontal axis will represent the reaction coordinate. So what we have here is we have the stage 1 is the alpha phase, and the beta phase actually with the lower gives free energy, right? So based on what you learned from previous slide, we can say because delta G, or delta G is smaller than 0, or you can say that because stage 3, the energy gives free energy on the stage 3 is smaller than that on the stage 1, so we can know the reaction direction definitely from alpha phase becomes to beta phase, right? But this is what we learn from or determine from the thermodynamics, right? But here we don't know the reaction rate, how fast the alpha phase will become to beta phase. So that will depending on the energy barrier or activation energy shown in here. That means the energy difference or gap between the stage 1 and stage 2. So here I put some description here. The rate of this kinetics process, which will involve the certain flux of physical entity, is determined by what? This will be determined by the driving force, which we involve here is a delta G. And the second one, which is more related to material property, we call the transport resistance or inertia of the system. This part will be, in this case, will be the energy barrier. So in order to emphasize how important, why the kinetics process is so important, so I'm giving you the other examples will be to explain this. As you know, the diamond, which with a sp3 carbon, is metastable at pressure equals to 1 atm and at room temperature. sp3 diamond is metastable compared to sp2 carbon, for example, like the graphite. So diamond is more metastable, but graphite at these conditions actually is more stable, right? So based on this, we can consider the sp3 diamond will be with a higher free energy here at 1 atm and room temperature, and the graphite sp2 carbon with a lower free energy will be like this, right? So based on thermodynamics, we believe diamond will convert it to graphite. But in our experience, we didn't have time, or we don't have any chance to visualize our diamond ring becomes to graphite ring, right? So what happened or why? So the point would be the thermodynamics only tell you the direction of chemical reactions, but it didn't tell you the rate of this chemical equations or chemical reactions. In this case, for the diamond becomes to graphite part, the key point here will be the energy barrier is very, very high. So with a higher energy barrier for transformation from diamond to graphite, so that means the reaction rate is very, very slow. Right? So let's explain why we don't have chance to visualize our diamond ring becomes to graphite ring. So next, I'm going to talk more about the energy barrier here. So, but before that, we only want to explain, give you the other example to explain these cases. The delta G, the driving force can be in diffusion in solid materials, can be the temperature gradient, can be the electrical potential gradient, and also can be the chemical potential gradient. And if the driving force is temperature gradient, so the flux will be, that will drive the heat flow or heat flux. If the driving force is electrical potential gradient, that will drive the electrical current or electrical flow, or you say electrical flow. If there's a exist of the chemical potential gradient, so that will drive the mass transport, or some people call that diffusion, atomic migration, or atomic transport. It's some kind of mass transport, right? Okay, so this is about the driving force. And the energy barrier part, when we talk about the energy barrier part, and which will affect determine the rate of kinetics process. So people usually will, if you want to speed up these reactions or this kinetics process, what can we do? There are two methods to speed up it. The first one would be what? Because it's an energy barrier, it was this high, right? So probably we can try to lower the activation energy or lower the energy barrier by ending the catalyst. So that will allow more reactants to become the product because energy barrier decrease, right? This is the first choice to speed up the reaction kinetics process. And the second choice would be what? Would be we don't touch or we don't tune the energy barrier. What we do here is we try to increase the numbers of reactants can have a sufficient energy to overcome this energy barrier. We want to increase the numbers of reactants. So the easiest way is increasing the temperature. Thermal temperature will allow more reactants have sufficient energy to overcome this energy barrier. So let's take a look on the Maxwell-Boltzmann distributions here. The vertical axis is the fraction of molecules, and the horizontal axis actually is related to the kinetic energy. And the blue one is a lower energy or lower temperature. And when you can, here you can see that when we increase the temperature, then there's more molecules can overcome with a sufficient energy to overcome this energy barrier compared to that in the lower temperature. So increasing the temperature is an easy way to allow more reactants have more higher energy, kinetic energy, which have chance to overcome this energy barrier. Okay. Next slide. As you know that we have two important factors to affect the kinetics process. The first one is the driving force, and the second one will be the system, inertia of the system. But sometimes the things is not just a simple one-step process. sometimes let's involve like two process, chemical two reactions, and so things turns to a little bit complicated. So I'm going to give you an example here. So in this slide, we are going to introduce you some related to the melting process. And this melting process actually involves two-step process. So let's take this as an example here. Now we have a small ice cube and put into the thermal isolation containers. And the other example will be I have a larger ice cube, but I put them into a container without any thermal isolation. And after one day, and I observed that in this case with a small ice cube one, we can observe the ice cube gets smaller, becomes smaller, and you also can observe some water inside these containers with thermal isolation. But in this case, even though I have a larger ice cube, but after the same time of period, all the ice melt into liquid. So what we have actually is the water only. So this actually is a melting process, right? So in this case, what this case tell you? Even though in this case, in the beginning, this ice cube actually is larger than this one. But after certain period of time, usually you will expect it what? The one with the larger ice cube, probably this one, you can visualize some small ice ball or ice tube in the meantime, right? But however, it all becomes liquid, becomes water. So this case tell you what? Tell you that in this case, melting process actually this is not a one-step process. Actually, it involves two steps. The first one is absorb the heat from the surroundings or from the environment. So which we will call that is a thermal transportation or thermal transport from surroundings. As long as it absorb some heat from surroundings, then the water H2O or water molecular H2O molecules will diffuse or be transported from the solid phase becomes to the liquid phase, which we call structure randomization, right? So it will involve the molecular transport. So when we talk about the melting process, actually it involves two steps, and it is really a serious reactions. Serious reaction means the first one is absorb the heat, and the second one is mass transport, right? And this is a serious process. And some case, which for example, like there's the other for the serious process, which usually the slowest one dominate the rate of the process, kinetics process, right? And as you learned before, actually we have the other kind of process, which we call a parallel process. The parallel process, for example, like when you end the catalyst one, when you end the catalyst in this chemical equations or reactions, and that means in the meantime we provide the other chemical equations with the lower energy, or we provide the other path for the reactants with the lower energy barrier ones. So in these reactions, or in these reactions, actually there are two paths, right? One with a higher energy and the other one has a lower energy. In this case, we call it as a parallel reactions. In parallel reactions, when you want to estimate the rate of this kinetics process, the faster one dominates, right? So I'm going to give you a summary of the kinetics. Kinetics, actually, you need to consider the time-dependent state function change process. And this process definitely is deviated from equilibrium state toward to equilibrium state, and the path we choose and the corresponding rate involved. This is a kinetics process. And which parameters is going to affect the kinetics process will be the driving forces and also the transport, mobility, or resistance involved, or some people will call it as inertia of a system. And the third one, important part, is what we mentioned in the previous slide, is in some cases, if the reaction you are interested in, or the kinetics process you are interested in, is not only a one-step process, it involves two reactions or two or more reactions, then in these cases you need to consider, is it a serious process? Are there a serious process or a parallel process? In serial process, for example, like the melting process and certifications, then you need to consider the slowest one in the serious process will be the rate limited step. If the kinetics process we're talking about is a catalyst process, it is a parallel process, right? So the faster one will be the rate limited step. Okay, so this is important to deal with if your kinetics process is not just a one-step process. So you need to determine, is it a serious or parallel process? Oh, the last one actually is talking about the thermal energy. So by using the Maxwell-Boltzmann distribution, if we know the temperature, then we can estimate how many or what's the fraction of the reactants have sufficient energy to overcome the energy barrier. So we can do some estimation based on these distributions. Okay. So next, we finish the first sections, and I highlight some important part here. So next, I'm going to move toward to the second sections, which we call about the difference between the equilibrium state determined by thermodynamics and the steady state in kinetics. Okay. So the thermodynamic equilibrium, actually we already defined that in previous slide, but we just, in order to explain the difference between the equilibrium and steady state, so actually I also put the similar slide here, but I just want to highlight some important part here. So the thermodynamic equilibrium, the important part would be the state function does not change with time, is the first part. And also, the chemical potential everywhere are the same. So there's no spatial variation in the system involve the chemical potential. So means the chemical potential everywhere are the same. So the second part will be the free energy of the system is minimized at the equilibrium state. So as we mentioned before, when a system reaches thermodynamic equilibrium, so the first one is there's no spatial variation in chemical potential. Based on this, because the chemical potential are the same everywhere, so there's no net mass transport. And the second one will be the total free energy is minimized. So if you want to do something, apply something on the system, then that means any movement will raise the free energy of the system. So the total free energy of the thermodynamic equilibrium is minimized for sure. So next, I'm going to provide you two examples, and hope you can determine whether they are in the thermodynamic equilibrium or not. The first case would be like now we have a material with a curve. We have a materials with curvature like this. So you can observe you can have the convex region and concave region like this. So the question will be, is this materials is under the thermodynamic equilibrium? So I highlight the criteria for thermodynamic equilibrium, right? The first one, you need to, if it is equilibrium conditions, it need to, right? The first one will be no spatial variation in chemical potential. So let's take a look on the chemical potential part. If I have if atom A, right? Atom 8, the potential of atom 8 at the convex region here expressed like this, equals to the chemical potential of atom A at the flat surface or on the flat surface plus the extra term. The term is the gamma surface energy. Omega is the average atomic volume. And the kappa 1 plus kappa 2, kappa is the curvature of these materials. So here we got the potential, surface potential of atom A at the convex region. And we want to, here if there's an atom at here, so it's at the concave region, and the potential, surface potential can express like this. And also the mu A0 is the chemical potential of atom A on the flat surface. Minus this is plus, and plus the extra term, and here is a minus extra term, and the term actually is the same with this one. It involves the surface potential or surface energy, average atomic volume, and also the curvature here, right? So based on this, let's definitely for sure the surface potential of atom A will difference on this curved surface, right? So the atoms at the curved surface varied with curvature, right? And I just want to remark what is the kappa 1 and kappa 2. When we want to describe a curvature or curve plane, then we will use this kappa 1 and kappa 2 to describe this curve plane or curve surface. So back to here, we will say the state of this material, so all the materials we have here actually is not in the thermodynamic equilibrium state, because the surface, we observe the spatial variation in surface potential, because this one is definitely not the same with this one, right? At this location, right? So here the driving force will be what? If you check this, you find that the energy of atom A at the convex region will be larger than that on the concave region. So there's definitely a surface potential gradient involved here. And as you know, the system tends to decrease the total free energy of the system. So the atom definitely will be pushed toward to the Keff region. So the driving force here will be the surface potential gradient, and the inertia of the system will involve what? Because the atom is going to push, right? So will be the mass transport, right? So the material property related to the mass transport will be the diffusivity here. So the inertia of the system actually here will be related to the diffusivity of these materials. And the surface here is you got the driving force and inertia of the system, and finally definitely will minimize the surface chemical potential or surface or the total free energy of the system. So in this case, we know that definitely mass transport or the atomic flux from here toward to here. So that will result what? The surface planization. So the curve surface will become too flat, and the flat will be reach the thermodynamic equilibrium. If I have a flat surface and there's no spatial variation in surface potential, right? Okay. So the other case will be the grain growth case. As you this is some pictures, and as a function of time. So here you can observe the grain get larger and larger. These grains get larger and larger, which we call a grain growth. So in this case, my question is also the same. Is it in the thermodynamic equilibrium state? So here we need to look closely on these polycrystalline materials. And we assume the isotropic grain boundary energy here. So next I'm going to say if you put if you pay attention on this polycrystalline grain, you have a grain and grain boundary, right? And the energy, from the energy point of view, if I have an atom at the grain boundary, the energy of the atom A at the grain boundary is definitely higher than that in the grain. So in this case, you know the energy of the grain boundary is larger than that in the grain, right? So in order to, in this case, you observe the energy difference, right? In the grain boundary have a higher energy, and the grain have a lower energy. So it's definitely a spatial variation in energy part. So here, probably if you want to emphasize what is a driving force, I would say probably it's energy gradient. And the grain growth actually also involve the mass transport, so the inertia of the system will be the diffusivity of the materials. And the final goal here, even though it is not in equilibrium conditions, but it also will go to the process will minimize the total free energy of the system. So the way to minimize the total free energy of a system is to decrease the volume fraction of grain boundary. Because the grain boundary have higher energy, so if you want to decrease the total free energy of this material system, so definitely you need to decrease the volume fraction of grain boundary, right? The only way to decrease the volume fraction of grain boundary is what? It is what? The grain growth, right? So the number of the grain will decrease, but the total the grain size will increase. And in the meantime, because the grain get larger and larger, then so the volume fraction of grain boundary will decrease in the meantime. Okay. So both these cases belongs to kinetics process. Okay. So I'm going to give you a short summary to identify the equilibrium state and the steady state. Equilibrium state condition defined by thermodynamics actually tell us the state function f. The state function does not change with time, and also there's no driving force involved in this system. So there's no driving force, so we also cannot observe any mass flux, heat flow, or any electrical current passing through our systems. Under these situations, we will call that it is equilibrium conditions. But what is a steady state? Steady state also, the state function does not change with time, the same with that in the equilibrium conditions. But in steady state, there's definitely a driving force exists in the system. You have a driving force, so you definitely will measure or observe the flux. So we will observe the constant mass flux. If we have a driving force is a chemical potential gradient, and probably you will have a constant heat flow, then the driving force will be the temperature gradient, right? So the steady state, actually the driving force here is a constant driving force. So you will get the constant flux, no matter it's a mass flux, heat flux, or the electrical current. This is the first criteria. And the second one is when you try to remove this driving force, then the system will goes from the non-equilibrium state to the equilibrium state. Okay, so this process is a kinetics process. So this is a steady state, right? And we have a constant driving force will cause the constant flux. But the other term, probably some people will ask about how about if I apply a force which is not a constant force, is a time dependent driving force. That means the driving force will change with time. So you definitely will get the time dependent flux. If we talk about the diffusion in solid materials, that will be related to the time dependent diffusion equation. So in this case, we will call this kind of situation will be the non-steady state, because you have a time-dependent driving force applied on the system, which will result in the time-dependent flux. Okay. So next, I'm going to give you two examples to will describe the steady state, including the heat flow in steady state and the mass transport or atomic flow in a steady state, and hope you can have more idea about a steady state. So related to the heat flow in a steady state, heat flow, so I'm going to use the state function temperature T as a quantity to describe this process, kinetics process. Okay. And what we have is we have the temperature is a state function to describe the system. And what we have here is we have a metal bar here, and I put a heat reservoir at the left-handed side and put the cold reservoir from the right-handed side. And this heat reservoir will supply the heat, and the cold reservoir will absorb the heat. So as long as the heat in equals to heat pump out, and it means this system will reach the steady state. At this moment, when you use the thermocouple to measure the temperature distribution along this metal bar, then you will get this curved. The vertical represents the temperature, and the horizontal axis means the location. So we are going to have this temperature profile when it reaches steady state, and this temperature profile does not change with time. Under this situation, we will say this is heat flow in steady state. Okay? And so the heat flow does not bring the system from one state to the other one. This means the temperature profile does not change with time, but it to exist the driving force, right? It's a temperature gradient exists on or apply on this system. So let's check whether this case is really the heat flow in a steady state. So there are three criteria. If it is a steady state, it need to satisfy these three criteria, right? The first one in previous slide we talked about, if it is a steady state, so the state function does not change with time. Yes, because the temperature, this state function does not change with time, right? And the second criteria will be we can observe the heat flux and also the driving force. So yes, we observe the heat flow, right, passing through these materials, right? And we also observe the temperature, the driving force, which is a temperature difference apply on this metal bar. So yes, we have observed the heat flow and also the driving force exist or apply on the system. The third one is when I remove the driving force. It means I take both this vector field out, then the system definitely will go to the equilibrium conditions, which means the temperature will become uniform along these materials, right? So it will go to the thermodynamic equilibrium. So I will say this case actually is the heat flow in a steady state. Okay? And the second case we will talk about is a mass transport part is also in steady state. And here we talk more about a non-steady state part. Okay. So before we move to steady state and non-steady state involved in mass transport or involved in diffusion, first of all, I will ask you, can you derive the fixed second law? Because when we talk about the mass transport, usually the two laws come out from your mind will be the fixed first law and fixed second law. And I believe you know the fixed first law, so my question would be, can you derive the fixed second law? Fixed second law actually is derived from the mass conservation. These equations. So I'm going to give you a brief review for this part, how to derive the fixed second law. Then we back to explain this idea, right? Okay, so let's take a look on these figures. Now I have a system. It's this cubic. So what's the mass conservation? Means the mass change rate inside this system will be equals to the mass transport in minus mass transport out. The residual part will be used to increase or change the mass change rate in the system, right? So I can express like this. I can write it down like this is a mass change rate, right? And we use the mass flux or the mass flow in minus the mass flow out. So this will be the mass conservation. And I want to express like related to the concentration part. So we also can express like this. It's a partial C, partial T is the concentration change with the time, right? And compared to this, right? This is a concentration. This will be in the mass per unit volume. So I times the volume of the system will be the A times this. The area times this. Delta X is the volume. So I use the partial C times the volume. What we get here is a mass. So it's a mass change rate, right? So you focus on here, this this equation here, we delete the a together and move the delta x to left-hand side. So what you get is flux Jx minus Jx plus delta x and divided by delta x. Actually, this minus flux gradient. It's a left-handed side. And right-handed side, what we have is a partial c, partial t. It's a concentration, how the concentration change with time. So this is a fixed second law. Okay? And next, I'm going to move back to talk about a steady state and non-steady state. So what's a steady state? As we mentioned, you have a constant mass transport, then under the constant driving force. So everything is constant, so it will be the time independent concentration profile. What is the time independent concentration profile? Means the partial c, partial t equals to 0, right? But let's do exist a concentration gradient. That means there's definitely a concentration profile, right? Exist on your materials or inside your materials. And due to the partial c, partial t equals to 0, so if you back to this fixed second law, this part equals to 0. So you can write it down, this part equals to 0. And the J here, we use the minus diffusivity times the concentration gradient, which is the fixed first law. So based on this, what we got is here. And we assume the diffusivity is a constant. We take the diffusivity out. So what we have is a diffusivity and a concentration. And next, what we have here is we have a second order derivative with respect to x. We got this right? So as long as you solve this differentiation equation, then you can have a concentration profile. So this is a time-independent concentration, right? So the concentration profile only change with location, and it does not change with time, okay? So this is we call a steady state. But how about if what we deal with is a non-steady state? Means what? Means the concentration profile does change with time. This part is change with time, so this one is not big. It's not equals to 0 anymore. So we need to solve this differentiation equation with 2 parameters. And also we assume the diffusivity equals to constant. So take this diffusivity out. So what we have is this equation, differentiation equation with 2 parameters x and t. So as long as you solve this equation, you can get you will know how the concentration of diffusing atoms change with location and time. So this is the other example to tell you the steady state. What's the mass transport in steady state and non-steady state? So now I'm going to give you a quick summary about the difference between the equilibrium state and steady state. The equilibrium conditions, actually the state function does not change with time, and we cannot observe. We don't have any driving force applied on the systems, and definitely for sure there's no corresponding flux involved. And all these are defined by thermodynamics law, so no net flux. And the steady state function also does not change with time, but we can observe there's definitely a constant driving force applied on the system. So this will result in the flow process. And in order to solve this one, we also assume this is a local equilibrium conditions, so that this will allow us to use all the state functions or equations we derive from thermodynamics. And based on this, we know the concentration determined because it's steady state, so the concentration profile definitely does not change with time. So it will be the time-independent diffusion equation, like this. So after solving this differentiation equation, so we are going to we will know the concentration profile, how the concentration change with location inside your materials. And the last one will be the non-steady state. The state function does change with time. So we have a time varying driving force. So that will result in the time related concentration profile. So what we have here, so after solving this differentiation equation, we will get the concentration the profile will change, how the concentration profile change with location and time.